Well, welcome to Chapter 4, and this section is 4.1, where we're going to discuss the concept of the function. And our objective will be to identify a function, to determine the domain, range, and zeros of a function, and to graph a function. Oh, there's a lot there, all right. And, functions can be kind of abstract when you're in algebra, but, we get to this level of pre-calculus and we have to have this stuff mastered. So don't be shy if you have any questions. Let's make sure we have the concept of function down. So here's your definition of a function right here. A function is a rule that assigns to every element in a set D exactly one element in a set R. And you guys know I am very visual, so I want a picture of this. Please add this picture to your notes. So one more time. A function is a rule that assigns to every element in a set D. So let's start with a set D. Now we're talking about every element in this set D. Every element. And we like to call those elements x's. So there is one element x in the set D. And what are we going to do to that x? We're going to apply some function to it. All right? And so what happens then? All right, well, that gives exactly one element, and we like to call this, so we had x in this set D that we applied a function to, so we're going to call that then f of the x. And that's the concept of function notation right there. And this f of x will end up in a set R. Now, I want you to think, why did we call all of our x's elements in a set D and all of our f of x's elements in a set R? Well, the set D is called the blank of the function, and I think you know D, domain of the function. The set R is called the R, that's the range. All right, so the set D would be all of my inputs of the function, and the set R would be all of my outputs. And that's the concept of function right there. Now, let's first talk about domain. You guys have been doing domain for a long time, so this should be really easy. All right, this is a rational expression because it's a fraction. All right, and can I just put any element x in the whole set of real numbers I want into that? Now think about that. What number can we not divide by? You can do it. Okay? Well, if x were 7, wouldn't I have 7 minus 7 or 0 in my divisor? And I cannot divide by 0. So I know that x can be any real number, but x cannot equal 7. And that is appropriate for expressing the domain. If you say x does not equal 7, that implies x can equal any other real number. Now, we have some real fancy notation for that I'd like to introduce here, and you're welcome to use it, but as long as you can communicate the domain to me, okay, we will be fine. Check out the official notation, though. It's really cool. Okay, D for domain is, and notice the birdie brackets, we use birdie brackets for set notation. So D is the set. And then what do we have in this set? We have x's. And this slash right here means such that. And where are our x's? They are in the set of real numbers. So x is in the set of real numbers. And that's what that double bar R stands for, the set of real numbers. Such that x cannot equal what number? X cannot equal 7. So there's your official notation. But if you tell me x cannot equal 7, I know that x can be any other real number. Let's do one more. Okay, h of r equals the square root of 1 minus r squared. Well, notice the radical. All right, and you guys have already studied complex numbers. Now, when we're talking domain of a function, that's what we're going to see if we graph it. All of the x values, or in this case, r values, because r is the independent variable. All right, so, all right, to keep this expression in the set of real numbers, wouldn't 1 minus r squared have to be greater than or equal to 0? 1 minus r squared is greater than or equal to 0. If r minus 1 squared were less than 0, we would have imaginary or complex numbers. All right, so let's solve this. So add r squared to both sides. So 1 is greater than or equal to r squared. Now, you know, this gets complicated to solve by square rooting both sides, but look at this. It's so easy to see. All right, what are the numbers that I can square and get an output that is less than or equal to 1? Well, think about that. I'm picturing a number line right now. And notice my endpoints, -1 to 1. Do you agree that if I square any element in the closed interval from -1 to +1, any x value in this interval, if I square it, I'm going to be still less than or equal to 1. So my domain is, well, what? -1 has to be less than or equal to, and remember, don't mix up your variables, we're using r's here, r, and r has to be less than or equal to 1. Anything outside of that closed interval will not work with this radical expression right here. Now, your fancy notation too, we could do it like this. The domain is the set R such that R is in the real numbers, and then you put your double inequality right here, where -1 is less than or equal to R, and R is less than or equal to +1. Okay, now, let's say they give you a graph, and they ask you for the domain, the range, and the zeros of said graph. Well, let's read this. Analyzing the graph of a function. 1. The domain of y equals f of x is the set of x coordinates of points on the graph of f. So we're talking about all of the x coordinates on this continuous curve. And this is a half closed interval right here. Okay? Projecting the graph of f on the x-axis gives the graph of the domain. So if I take this graph and I project it down onto the x-axis, well, I'd have a closed dot at x equals 2. And then I'd have an open dot at x equals 3, 4, 5, 6. And the graph is everything in this half closed interval from 2 to 6. So we're going to write that as 2 is less than or equal to, because this is closed, x, and x is, now this is open, so less than, and less than what number? 6. And there's the domain. And if you just give me that double inequality, I am fine with that. Now, the range. The range of y equals f of x is the set of y coordinates of points on the graph of f. So we're talking about all of the y coordinates on this curve right here. So guess what? Could we project the graph onto the y-axis to see the graph of that? So projecting the graph of f on the y-axis gives the graph of the range. So let's project and write down our range. So let's see. Talking everything in this interval, and I have a closed dot at, it looks like y equals 2 right there. So there's my interval. Closed dot right there with some very fancy animations. And what is this going up to? Well, it looks like it's going up to 3 to me. So I'll put an open dot at the 3 right there. And there's my graph of the range. So let's write this as an inequality. So 2 solid dot less than or equal to, and we're talking range y's y, and y is open dot less than what number? 3. Okay, so there's the domain and the range by simply projecting the graph onto the x-axis for the domain and the y-axis for the range. Now, last concept here. The zeros of y equals f of x are the x-intercepts of the graph. So, does this curve ever touch the x-axis? No, it does not. So guess what? What are the zeros then? Well, it never touches the x-axis, so I'm going to say the zeros would be the empty set. And that's birdie brackets for set notation with nothing inside. That is the empty set. There are no zeros. You could also, if you prefer, just say D&E does not exist. Okay, thank you. Okay, so given the graph of a function, can you give me the domain, the range, and the zeros of said function? So let's practice this with a couple more really cool graphs. Our first graph, oh, look at that. Wow. That's not your typical exponential or linear function that you're used to working with here. We've got a few turns. Also, by the way, maybe a couple horizontal asymptotes, but we'll talk about those later. Right now, though, let's talk domain. Now, notice something here. Do you see the arrow going to the left and the arrow going to the right? All right. It looks to me like the domain would be the entire set of real numbers, because I'm going forever to the left and I'm going forever to the right. So all the x-coordinates on this curve would be the set of real numbers. Now, I better say this too. Sometimes they give you a graph where they only give you a window and they don't put the arrows at the end, but the arrows are implied. Try to be aware of that as well. So let's say that the domain is, and there it is, projected onto the x-axis, the set of real numbers. So x is in the set of real numbers. And the birdie brackets are set notation. If you just write x is in the set of real numbers, that would be fine. Now, let's project this graph onto the y-axis very carefully. So, looks like here's all the x values to me, right? So the range, there we go. But now, I want to check the endpoints carefully. Doesn't it look like y equals -1? It looks to me like they're trying to say that the graph is going to keep going and going and going, getting closer and closer to that horizontal asymptote, but never reaching it. So I'm going to say that's an open dot. Now, if you go up top here, it looks to me like the graph is kissing y equals 2 right there and then dropping down. So I think that's a solid dot up top right there. So I'm going to say that the range is the set y such that, and my lower bound is -1, and that's open, is less than y, and y is less than or equal to, because that's closed, and what number is that? 2. And there's my domain and the range. If you just give me the stuff in red, I will give you full credit. All right, now the zeros. Well, it looks like I only crossed the x-axis right there. And I want the zeros always written as ordered pairs. So that would be x equals 1, y equals 0. X equals 1, y equals 0. And there we go. That's the big concept of the day right there. Given a graph or a function, can you come up with the domain, the range, and the zeros? Okay, now, next one. Oh, this is a pretty graph right here. Okay, well, let's talk domain. Okay, and how about we project onto the, oh, be aware, u and v. Make sure you talk the language of the problem. So this is the u-axis. So the set u such that, and if I project onto the u-axis, so I'm going to have an open dot at u equals 1 and an arrow going to the right. Just like that, because it's going forever and ever and ever to the right. Okay, so that would be what? Isn't that nothing more than u is greater than 1? There we go, domain. Now the range. Well, it looks like I have a maximum, and then I'm going forever down. So the range is going to be, and we're talking about v's now, so the set v such that, and what is this v value up here at what looks to me like the max? 1, 2, 3. So I'm going to project, And I did a closed dot because it looks like I'm kissing that horizontal line right there and then going down forever. So that would be V is less than or equal to what number? 1, 2, 3. And now the zeros. This time I have 3 of them. Okay, and that would be what? The ordered pair 2, 0. And then this one would be a ordered pair 4, 0. And then finally one more, and that looks like a 6, 0. And there we go. Isn't that cool? All right, so let's talk about function notation to make sure we know everything we need to know about the variables. Okay, function notation. Well, when we have a function, we usually have a independent variable that's graphed on the horizontal axis and a dependent variable that's the vertical axis. Now in function notation, instead of going x and y, we go x and f of x because f is a function of x. All right, so look at this, c of g. Okay, that's function notation for the cost of gasoline based upon the number of gallons I pump. So c of g equals 3.29 times g. That means the cost in terms of the number of gallons of gas that I pump is $3.29 per gallon right there. But we need to know the language. So that c is my dependent variable because it depends on what? Cost depends on how many of gallons I pump. And g is the independent variable, the number of gallons. Because my cost function will be in terms of the number of gallons of gas that I pump, my total cost. Okay, we have a definition on this slide, and we're talking about a relation. Now, a relation implies any correspondence or rule that pairs the members of two sets, the domain and the range. So, isn't that what we were talking about earlier with the definition of a function? Because doesn't a function take an element in the set D and turn it into an output, which is an element in the set R? So, how is a relation different than a function? Well, what's happening here is a function is nothing more than a subset of the set of relations. This is a Venn diagram, you guys. Now, a function is a special relation. So a function would be something like, I don't know, y equals the square root of x. Now, I hope you guys are picturing y equals the square root of x right now. Let me give you a picture of that. There it is right there. This is your typical root function, or the parent function of all root functions right there. Y equals the square root of x. And that is a function. How do I know it is a function? Because every input x has one and only one output y. All right? And you can check that with a vertical line test. That vertical line, no matter where I draw it, is only going to cross that curve at one point. Now, a relation does not have to pass the vertical line test. So let me give you an example of a relation. How about if I change this y equals the square root of x to y equals plus or minus the square root of x? Now, again, the plus root x is this graph right here. And then if I take the opposite of that with this minus out front, that's just going to take this graph and have another branch that is reflected in the x-axis, so it'd be down below. All right, and that is a relation because there is a correspondence between two sets. You have all these x's, but almost all of these x's have what? Two outputs y. So if I draw a vertical line here, that graph does not pass the vertical line test because we have two intersection points. So when x equals approximately 1, 2, 3, 4, I have a positive output and a negative output. That is a relation, but it is not a function. Functions must pass a vertical line test. All right. Wow. X squared y equals 4x minus y. Well, I'm betting they want us to determine whether or not this is a function. And that's a pretty scary little equation there. I'm going to give that the wow again. So if you get something like this, how are you going to determine whether or not it's a function? Well, I would hopefully be able to solve for y and then use my calculator to graph it. So let's see if we can solve for y. Well, if you're going to solve this for y, wouldn't you want, first step, get your y's on the same side? So could I add y to both sides of this equation? That would give me x squared y plus y equals 4x. Now, let's factor the common factor on the left of y out of both of those terms. So y would be, and y times what will give me x squared y? X squared. Y, x squared is x squared y. Plus y, so y times what will give me y? Well, that would have to be a plus 1, and that equals 4x. Now, to solve for y, we undo this multiplication, so let's divide both sides by the quadratic binomial x squared plus 1 to get y equals 4x divided by x squared plus 1. Now, I don't know what this graph looks like, but I have a great graphing calculator, so I'm going to use that. And I put this onto my graphing calculator, and there's my graph right there. Okay, beautiful. That's actually a really nice graph too. Now, my question is, does every input have one and only one output? Well, let's break out our vertical line. Could I put a vertical line anywhere on this graph that's going to cross that graph at more than one point? It does not look like it to me, so I'm going to say that x squared y equals 4x minus y is a function. All right, let's do one more. Oh, by the way, I want to add something too. This function is not, and this is where we're going to go down the road a little bit, all right? It's not one-to-one. And here's what I mean. We're going to have what's called a horizontal line test too. Now, do you see that this horizontal line crosses the graph at more than one point right there? So I have an output with more than one input. It's kind of the opposite of the vertical line test. And that makes sense. Horizontal line test, opposite of the vertical line test. Anyway, what that means is that this function, it is a function, but it is not one-to-one, which means it does not have an inverse, which we're going to get into later. Now, the next relation right here, y squared equals 4x squared. And notice how I called it a relation. It may be a function, but to determine that, I better solve for y first. Okay, so if I'm going to solve for y, I'm going to take the square root of both sides. So the square root of y squared is y equals, and now I'll take the square root of each term here. The square root of 4 is a 2. Oh, and don't forget your positive and negative roots here, and then the square root of 4 is a 2, and the square root of x squared is x. So square root of both sides, I get y equals plus 2x or minus 2x. Well, picture the graph of y equals 2x. That's a line going through the origin with a slope of 2. Picture the graph of y equals negative 2x. That would be a line through the origin with a slope of negative 2. So if I graph that on my calculator as two separate graphs, it would look like this x right here. And does every input x have one and only one output y? No, because look at that vertical line right there. Does not pass the vertical line test. So this is not a function, but there is a correspondence between a domain and a range, so we call that a relation. Remember, a function is a relation, but a relation does not have to be a function. Okay, now we've verbalized this several times, but here it is official. The vertical line test. If no vertical line intersects a given graph in more than one point, then the graph is the graph of a function. So that's today's lesson. You guys, I'd like you to do page 122, 1 through 17 odd, and then number 23. And you guys have a great day.